Hi, welcome back to educator.com. Today we're going to talk about the fundamental theorem of algebra. This lesson is not going to be like a standard lesson. So normally we see some interesting ideas and then we look at how numbers interact with those ideas and then we start working out examples. For this lesson though, we're going to just see interesting ideas. There will be hardly any numbers and there will be no examples whatsoever. Why? The ideas we're about to see are from advanced mathematics, and they're more about showing fundamental truths than just giving us a bunch of numbers and exercises to work with. Furthermore, since they don't really involve numbers, most teachers and textbooks can't and won't. They just won't be able to test this stuff, and instead they only briefly mention it. So why are you still watching this lesson if you're never going to be graded on it? Because this stuff is cool. At least I think so. You're about to see some amazing results from really high-level mathematics, and you're going to be able to understand it. You're actually going to be able to understand this stuff from what you've just seen in the previous lessons on polynomials. So it's a really cool chance to have a culmination of understanding and be able to get something pretty advanced from, a level that's not super difficult to understand. If you've got the time, humor me and watch this. You might find it interesting. I think it's pretty cool, and I hope you do too. Thanks. All right. Previously, we've seen that while some polynomials seem to have no roots, they can actually have hidden roots, in a way, in the complex numbers. So, for example, if we look at x squared plus 1 equals 0, there's no solutions to that, right? X squared plus 1 has no roots in the reals. If we look at its graph over here on the reals, we see that it never manages to cross the x-axis, so it has no roots. But if we switch into the complex numbers, we find roots, right? We find I and negative I work. For example, I squared plus 1 becomes negative 1. I, the imaginary number squared, becomes negative 1 plus 1, so we get 0. Hey, look, that's a solution. Same thing would happen if we took negative I and squared that. So this realization that there are roots, even though at first it doesn't seem like there's roots, might give us this sneaking suspicion that all polynomials have roots if we allow for the complex numbers, that there's some root out there that we might not be able to find using the real numbers, but that it is out there when we expand our search to the complex numbers. At least we'd have this suspicion. It turns out that our suspicion was correct. This idea is expressed by the fundamental theorem of algebra. It's such an important fundamental idea about how polynomials work that it gets this name, fundamental theorem of algebra. And it says that every polynomial of degree n greater than 0 has at least one root in the complex numbers. Notice that it's at least, so it could have more, and it also says complex numbers. So every polynomial that isn't just a constant, that has a degree of 1 or greater, has at least one root. So we're guaranteed a root in the complex numbers if we expand our search to the complex number. This seems like a pretty simple idea, probably, but it's actually very difficult to prove. The proof requires advanced mathematics, and so we won't be able to see it here in this course, but trust that it is true, and it can be proved if you get to a high enough level and have enough background. So at this point we might say, well, where are all the imaginary roots? Considering the fundamental theorem of algebra, why haven't we seen more imaginary roots? If we're guaranteed, what that says, why is it that x squared minus 4 equals 0? Why do we get only the roots of 2 and negative 2, right? Those don't use imaginary numbers. It seems that we're just fine without imaginary numbers. We can find roots just fine. So what is up with the fundamental theorem of algebra? Well, remember, it didn't say imaginary numbers, it said complex numbers. It's the complex numbers. Now, by definition, a complex number is of the form a plus bi. So notice, if we felt like it, we could say b equals 0. And if b equals 0, then the complex number is all real because we'll be left with just the a portion, and a is just a real number. So we see from this that the reals are a subset of the complex. The reals are contained in the complex numbers. The complex numbers have all of the real numbers inside of them because we can just cut off that imaginary component by setting b to 0. So the above solutions of x equals 2 and negative 2, they are complex numbers because they fit in the a portion. They fit in the real portion of a complex number, so it's still a complex number. We can show all real numbers as complex numbers, so that's what the fundamental theorem of algebra is telling us. It's telling us that the roots are going to be complex numbers, but since it's a complex number, it could just be a real number. Just like all integers are contained in the real numbers, right? You can be a real number, but still be an integer. You can be a complex number, but still also be a real number. All right, with the fundamental theorem of algebra under our belts, we can now go on to the n-roots theorem, which is also sometimes called the n-zeros theorem or the linear factorization theorem. A polynomial of degree n has exactly n roots in the complex numbers, and these roots are not necessarily distinct, so they're not necessarily going to be different from one another, and we'll talk more about all of these things. Another way to say this is that for any polynomial p of x, a polynomial p of degree n greater than 0, there exist n complex numbers z1, z2, up until zn, so just n complex numbers, and each one is going to be some z. And they're also, once again, not necessarily distinct. z1 is not necessarily going to be different than z2. We're just guaranteed that there will be a total of n numbers. And a constant number a, such that the polynomial is equal to a times the factor x minus z1 times the factor x minus z2 times the factor x minus zn. That is a way of saying that we can break it into a bunch of linear factors, right? Since x minus just some number is a linear factor, we can break any polynomial into n linear factors. Impressively, we'll actually be able to prove this theorem from what we currently know. We're going to see a sketch of the proof after we discuss what the theorem means, and it's pretty cool that we can actually see how such an advanced piece of, mathematics can be proven from fairly simple things, assuming we can assume the fundamental theorem of algebra. First comment is multiplicity. We need to notice that a polynomial of degree n has n roots, but that they're not necessarily going to be distinct. For example, if we consider f of x equals x to the fifth minus 5x to the fourth plus 10x cubed minus 10x squared plus 5x minus 1, and we factor it, we'll eventually figure out that that's x minus 1 to the fifth. Now, that means that when we look at it on the graph, it's got just one root, just one x-intercept, but in a way it's showing up 5 times. So f only has one distinct root at x equals 1. That root repeats 5 times, right? We've got it to the fifth. So we can break f into 5 linear factors, x minus 1 times x minus 1 times x minus 1 times x minus 1 times x minus 1. They're just all the same linear factor. This idea is called multiplicity, that we can have the same root show up multiple times. We can have the same factor show up multiple times. In this case, we would say f has a root at x equals 1 with multiplicity 5 because the same linear factor containing one root shows up 5 times when we break it into its factors, multiplicity. Complex numbers are necessary. It shows up in the statement of the theorem, but it's really important to be aware that this is only true, this n-roots theorem thing is only true if we're allowing complex numbers. For example, f of x equals x cubed plus 1, we can break into x plus 1 times x squared minus x plus 1. So x plus 1, that one has a solution in the reals. -1, x equals -1. But x squared minus x plus 1, that thing is an irreducible quadratic. It doesn't bring any real solutions. So if we restrict ourselves to the reals, f has only one root at x equals -1, if we're stuck just in the reals. But this theorem tells us that there must be an additional 2 roots, right? Because we started off at a degree of 3 in our polynomial. So since our polynomial had a degree of 3, we're guaranteed a total of 3 roots. And if we found that there is one root already, then we know that we can subtract one off, so there must be 2 roots left that we haven't found yet. So those 2 roots must be complex. In other words, the theorem guarantees n roots, allowing for multiplicity as we just talked about, but only if we're using the complex numbers. If we restrict ourselves to the reals, we won't necessarily be able to find n roots. Complex coefficients are also allowed. It wasn't explicitly stated, but the n-roots theorem is still true even if the coefficients of the polynomial are complex numbers. For example, if we have this second-degree polynomial, this quadratic polynomial, 2 plus I times x squared plus -15i times x plus -7 plus 49i, well, 2 plus I, -15i, -7 plus 49i, those are all just complex numbers. And it turns out that the n-roots theorem is true here. We can break it into linear factors, 2 linear factors, because remember we started off with a degree of 2 on our polynomial. So we can break it into 2 linear factors along with some constants at the front. So 2 plus I times x minus 3 minus I times x minus 7i. So the degree of the polynomial is 2, and it has 2 roots, or we can look at that equivalently as being factored into 2 linear factors. So the theorem holds whether the coefficients of the polynomial are real or complex numbers. Pretty cool. Existence theorem. This is a really important idea. The fundamental theorem of algebra and the n-roots theorem are existence theorems. They guarantee the existence of roots. We know that there have to be n roots. However, they don't tell us how to find the roots. All they do is they tell us that they're out there somewhere. They guarantee existence, but that's all. They don't tell us how to actually find what the roots are. For example, we know that x to the 4th plus 1 equals 0. Since we've got a degree of 4, it must have 4 roots, but that doesn't actually put us any closer to figuring out what they are. All we know is that they're out there somewhere, but we don't know what they're going to be from these theorems. The theorem guarantees the existence, but it doesn't tell us how to actually get to them. That's an important point. All right, we can now actually see a proof sketch of how the fundamental theorem of algebra can be, sorry, not the fundamental theorem of algebra, how the n-roots theorem can be proven. The fundamental theorem of algebra, like I said, requires some pretty advanced, beefy mathematics. We won't be able to see it here, but we can actually understand how the n-roots theorem is being built out of the fundamental theorem of algebra. So, starting with the fundamental theorem of algebra, which we will not be able to prove, and the division algorithm, which we addressed earlier when we talked about polynomial division. The proof is within our grasp. So start off by considering some polynomial p of x with degree n greater than 0. Now, the fundamental theorem of algebra, remember that said that there is at least one root. So by the fundamental theorem of algebra, we're guaranteed there's at least one root. So let's give that one root that we're absolutely guaranteed, we'll give it a name, and we'll call it z1 because it's our first root. And we know that p of z1 equals 0, right? It's a root because if we plug z1 in, we get 0 out of the polynomial. So there's going to be at least one root to our polynomial p, and we'll call it z1. Now, from earlier work, we know that if we've got a root, that's the same thing as saying if there's some root that is, causes our polynomial to go to 0, that's the same thing as saying that there is a factor x minus z1 somewhere inside of our polynomial. So by the division algorithm, we know that there exists some polynomial q1, right? We'll just call it q for quotient, and then we'll need to give it a number because there's going to be a bunch of these quotients coming up soon. So we'll call it q1 of x because it's the first time we've divided our initial polynomial, and it's going to be degree n minus 1 because we're going to pull out x minus z1 so that we'll get x minus z1 times q1 of x, right? That we can pull out our factor because we were guaranteed this factor because we know there is a root of z1, so there must be a factor of x minus z1. So we can pull that factor out and we'll be left with that factor times some quotient. So we'll have x minus z1, the factor that we know must be inside because of the fundamental theorem of algebra. And then we pull it out through the division algorithm, and we must be left with some q1 of x. There can't be a remainder because we know that that factor must be cleanly in there. It must be able to divide out evenly, otherwise it couldn't be a factor. So we've got that our initial polynomial is equal to x minus z1 times some other quotient polynomial q1 of x. And since we pulled out a degree of 1 from a polynomial that initially started at n, we started at n and then we pull out 1, we know that we're going to have a degree of n minus 1 in our quotient polynomial. So we can keep going with this procedure, right? We did it once and we pulled out a root and then we broke our polynomial out. We knew that there was a root and then we were able to factor out that linear factor because of that root. So if we have n minus 1 greater than 0, remember, n minus 1 is the degree of our first quotient, we can use the fundamental theorem again, right? The fundamental theorem says as long as your degree is greater than 0, there's a root in there. So if that's the case, we know that there must be some root z2 where when we plug it into our quotient, remember, since n minus 1 is greater than 0, we can use the fundamental theorem of algebra to guarantee that there is a root z2 so that we plug it into our quotient, and so q1 of z2 is equal to 0. Cool. But we also know that z2 has to be a root of p of x because the way that we got q1 of x was by dividing it out. So we have x minus z1 times qx is the same thing as p of x. So if we plug in z2 into p of x, then we're going to have z2 plug in, right, for our x. And so we'll get z2 minus z1. And that's some number. But we're also going to have q1 plugging in the z2 here. So we knew that q1 of z2 equals 0, so that means that the whole thing has to come to 0 because we've got a 0 here, and 0 will knock out whatever else we have. So the whole thing comes to 0, which means that p of z2 has to equal 0. Pretty cool. Now, we can just use the division algorithm again. We know that q1 of z2 equals 0, so it must be the case that x minus z2 is a factor of q1 of x, right? Since it's able to be pulled out, so we can pull out a factor x minus z2 from q1, which gives us, once again, another quotient, our second quotient, so we'll call it q2 of x, and q2 will be a polynomial of degree n minus 2, because remember, q1 started at n minus 1, and then we're going to subtract 1 because we're pulling out a degree of 1. So we subtract 1, so we're going to get n minus 2 as the degree of q2 of x. Now, this means that we can also express p of x as x minus z1 times x minus z2 times q2 of x, right? Since q1 of x equals x minus z2 times q2 of x, and we know that p of x equals x minus z1 q1 of x, we take this right here, and we swap it in for q1 of x right here, and we're going to get this thing right here, x minus z1 times x minus z2 times our quotient 2, our second quotient of x. And we just keep going with this method until eventually the quotient polynomial, until we eventually get down to some qn that's going to just be a constant. We'll be stuck at degree 0. At this point, we'll have a total of n roots because we'll have pulled out one root each time we take a step down, and so we'll take an n steps down. We'll have managed to pull out z1, z2, all the way up until zn. Effectively, what we're doing is we're whittling down the degree of the polynomial we started with. So we're whittling down the degree. For every step we lower the degree by, we manage to get another root. If we start at degree n, that gives us n steps to go down, so we've got n steps to pull from, we manage to get n roots out of it. For example, let's consider if p of x is degree 5. So we start off at degree 5 with p of x, our initial polynomial. By the fundamental theorem of algebra, we're guaranteed that it must have one root, z1 we'll call it. Then we use the division algorithm to break it into q1 of x. Now, q1 of x is going to have degree 4, and so by the fundamental theorem of algebra, we're guaranteed another root, z2. And since z2 is the root of q1, and q1 is contained inside of our initial polynomial p, z2 must also be a root for p of x. Great. Now, we use the division algorithm again. We can break this down, and we're able to get to saying that q2 of x is able to come out of q1 of x, and it's going to have a degree of 3. By the fundamental theorem of algebra, we're guaranteed that it must have a root z3, and since q2 is contained inside of q1, which is contained inside of p, we know that z3 is once again a root for our initial polynomial that we started with. We then break down q2 of x, we get to q3 of x. q3 of x will now have a degree of 2, because we're stepping down once each time. Since it has a degree greater than 0, we're guaranteed a root there, which is once again going to be a root of our initial polynomial. We break it down once again, we get to q4 of x. It has a degree of 1, so it is guaranteed to have a root of z5. We plug that in, and so that's going to once again be yet another root. And finally, we use the division algorithm one last time, and we get down to q5 of x, which now has a degree of 0. And since we have a degree of 0, we're not able to get a root out of it, so I've used up all of our roots. So we've managed to pull out 5 roots because we start at degree 5, and each step we're able to pull out one root as we subtract by 1. And so we're finally left with some constant polynomial, and that's where our a, the a that multiplies the whole thing, that's going to be our 5th quotient polynomial at the very end. It's going to be a times x minus z1 times x minus z2 times x minus z3 times x minus z4 times x minus z5. Pretty cool. So really, really deep stuff from advanced mathematics that we can actually have a pretty good of understanding just from what we've managed to learn about polynomials so far. Pretty impressive. All right, we'll see you at educator.com later. Bye.